All right. Okay, so the last topic that we had to talk about for this chapter is atomic mass. We talked a little bit about the atomic mass of each of the individual subatomic particles. Remember, protons and neutrons, they're about the same, and then electrons are really, really light. But now we're going to talk about the atomic mass of an actual atom, not just its individual subatomic particles. And actually, this is more along the lines of a periodic table that you would find in your textbook compared to the ones earlier. Notice that it's basically the same. Let's zoom in on carbon again. But now it's got one extra thing down at the bottom, this number here. Okay, this number here is the average atomic mass. So if I took a scoop of carbon atoms and then took the average of the mass of each one of those atoms, I would get 12.0107 AMU. All right, so that's that extra bit of information that you'll find on most periodic tables. For those of you that took high school chemistry, you might remember something called an atomic mass, or I'm sorry, a molar mass, which is basically the same thing as an average atomic mass, but we haven't talked about moles yet, so we'll graduate there. For now, we're talking about as if I had, let's say, 100 carbon atoms. I took the mass of each of those and then averaged it. This is what I would get. Okay. So how does this work? Well, it's what's called a weighted average, but let's sort of get to there real quick. Let's think about just a normal average. Let's say that I had these two apples. Okay, and I wanted to know what the average mass of my apples were. I have two different types. One of them's bigger, one of them's smaller, but I just wanted to know on average, right? So I would take the mass of each of them, the 200 grams of my green apple, the 150 grams of my red apple, and then I would divide it by the total number of apples that I had, which would be 2, and that would give me 175 grams per apple. That's the average mass. Okay, but then what if I had like a much larger sample, like something like this, right? Now I have 10 apples. 2 of them are my 200 gram green apples. And then I have a full 1, 2, 3, 4, 5, 6, 7, 8 that are those smaller 150 gram apples. So then I would take 2 times 200, add 8 times 150, and then divide that all by 10, and I get now 160 per apple, right? Which is different than what I got above, because above they were equal. This is what's called a weighted average, where what's the weight is that number of apples that you actually have for each category, which was 8 compared, whoops, I used orange, to the 2 I had for the green apples, right? I had fewer green apples than red apples, so I used those weights, the 2 and the 8, in order to get a weighted average. All right. So how does this relate to what we're doing with the average atomic mass? Well, this is how it works. If I take a scoop of carbon, that consists of both carbon 12 and carbon 13, right? Carbon 13 is the larger one. And then, but carbon 12 is far more abundant. We have way more carbon 12 in the world than we do carbon 13. So I would take a weighted average where the weight is reflecting how much more of one I have than the other. Okay, and that's what gets me the number that was on that periodic table of average atomic mass. Okay. So first of all, the atomic mass unit that we talked about before, where a proton and a neutron were pretty much one, the strict definition of it is it's 1/12 the mass of a carbon 12 atom. Okay, so basically they took the mass of a carbon-12 atom, divided it by 12, and that's what they said was 1 AMU. So that means that the mass of a carbon-12 atom is exactly 12 AMU. Okay, it's kind of a finer point. I wouldn't stress too much about that. All right, now we're getting again to this average atomic mass. And again, the whole point is it's gonna be a weighted average, which takes into effect the percent abundance of each isotope, right? So now we got another sort of set of isotopes to look at. We got chlorine 35, and we got chlorine 37. If you looked at all the chlorine atoms on Earth, it turns out that 24.2% is chlorine 37, and 75.78% is that chlorine 35. So that's what we're going to try to account for in our calculations. Okay, and then the other thing is you'd have to be told what the mass of chlorine 35 is and what the mass of chlorine 37 is. So this number right here is the AMU of chlorine 35. And this right here is the atomic mass of chlorine 37. Okay, so if you were given those masses and these are the weights, then you could calculate what is the average atomic mass of chlorine. And so this 35.45 would be that number that was on the periodic table. Okay, and let's just notice how this weight here corresponds to this weight here. It isn't in percentage form, it's in what's called fraction form. So you take that 75.78% and divide it by 100, and that gives you the weight that you use. Okay, so that times the mass, the weight times the mass, plus the weight times the mass of the other isotope is what gives you your average atomic mass. Okay, and so we're going to do a few calculations with this here. Real quick, even before we get into the strictly doing the calculations, there's an almost easier type of problem that I would expect you to be able to do. And that is, given the average atomic mass on the periodic table, tell me which element is more abundant, right? So let's just do an example here. We're going to talk about neon. Neon consists of two different isotopes, neon 20 and neon 22. Which is more abundant? That's the question we want to ask. Okay, we can actually do this without knowing the average atomic mass exactly of each of these isotopes, because let me just point out something when we were talking about chlorine. Chlorine 35 has an average atomic mass. I mean, look at how long this is. There are a ton of digits given here. If we were to round to the ones place, though, this number is basically 35. It's not exactly 35, so when we're doing a calculation like this, we want to make sure to include that number with all of its digits. But if we're just going to approximate here, we could call that 35, and we would be pretty close. Likewise, if we look at the average atomic mass of chlorine 37, the other isotope, this is basically 37, right? Again, if we were going to do a strict calculation, we'd want to make sure to use the exact number. But if we're just looking for an approximation, we could use 37, okay? So that's what sort of the logic behind these problems are, is we're going to say that neon 20 has an atomic mass of about 20, and neon 22 has an atomic mass of about 22. And so really all we're going to do is we're going to look on the periodic table and see which direction that average atomic mass, or which one the average atomic mass is closest to, right? If the average atomic mass was 20 exactly, then there wouldn't be any neon 22. Likewise, if the average atomic mass was 22, then there wouldn't be any neon 20. what would the average atomic mass be if it was exactly 50-50 neon 20 and neon 22? Right? If we had exactly 50-50 distribution, we would expect the average atomic mass to be about 21, right? That'd be if it was exactly 50-50. So let's see, let's look at the periodic table and see. So first of all, we got to be able to find neon. So everybody take a second, see if you can't. Okay, neon is actually one of our Nobel gases up here. The average atomic mass for neon is 20.1797. So does neon contain more neon 20 or more neon 22? Which one's more abundant? All right, that number is way closer to 20 than it is to 22. So we know that there's way more neon 20 in the world than there is neon 22. Okay, so this is a simple kind of a simple analysis that you can do without having to do any math, just by looking at the numbers. All right, but now let's get into the more complicated. I went too far. Now let's get into the more complicated type of problem here. And first thing I wanted to do actually is use really clean numbers, because I think that one of the things that really is hard to wrap your head around with these problems are just how ugly those numbers look, right? I mean, I'll show you that the math really isn't too bad, but when you look at a problem like this, your eyes just go a little crossed with all those digits that are there. And again, that number was basically 35 and the other number was basically 37. But because we're good scientists, we have to use all of our digits. And that's really what makes these problems difficult, because the math isn't, it's just the big ugly looking numbers and how scary it looks. That's hard. So the first thing I wanted to do is a made up example that has really easy numbers. So this is going to we're going to take element X. And it's got two different isotopes. The first isotope is X20, and we're going to say that that has an atomic mass of exactly 20 AMU. All right, and then we have another element, or another isotope of element X, and that has an atomic mass of exactly 21 AMU. All right. And then we're going to make it even easier by saying that the distribution here is 50% element X20 and 50% element X21. So maybe even without doing any really hardcore pencil and paper math, you guys could already figure out what the answer is supposed to be. But let's actually put it into our formula. So it's going to be the weight times the mass of one. So this is, let me actually do this. This is isotope 1. And then you're just going to add the weight times the mass for isotope 2. And that will give you the average atomic mass. Okay, now remember, before we can use these percentages, we're going to have to convert them into fraction form. So 50.0% divided by 100 times the mass, and so this one will be, we'll say that isotope 1 is X20. So that's times, 20 AMU plus 50 divided by 100 times the mass of isotope 2, which is this other one, where we said the atomic mass was exactly 21. So you guys can punch this into your calculator, and what you should find is you get an average atomic mass of 20.5, and then we always have to make sure we include our units of AMU. Okay, so that's using you know, the math is going to be the exact same in our next example. It's just the numbers we're going to use are going to be a lot uglier. Okay, so let's actually copy. Okay, now our first isotope is going to be copper 63, which has an atomic mass of 62.929599 AMU and a percent abundance of 69.17. And our other isotope will be copper 65, which has an atomic mass of 64.927793 AMU and an abundance of 30.83%. Okay. Yes, actually, let me do this. Let's go ahead and do this example right underneath. It's kind of all explained out on these slides, but let's just set it up together. Make some room here. One of the things you'll find about these lecture slides is there's a lot of text on them, and that's kind of because they're meant for, you know, when you guys are looking through the slides on your own, there's this given explanation. I'm not going to read the text off the slides. That doesn't really do us any good, right? You can read it yourself. So I'm going to give you my own explanation as I'm doing these problems. And then those long drawn out sort of additional slides are there for you when you're going back and doing these problems on your own. Okay. So this was our, I messed up my colors, whatever. I'll just stick to the colors that are there. Okay, so here we're going to say isotope 2 is, this is our copper 63. This is our copper 65. And you're kind of swapped, but it doesn't matter as far as the math is concerned. Okay, so the first thing I got to do is put my weight and then multiply it by the mass, right? So in terms of, again, if we're going to say, look at copper 65 first, the weight, I have to take that percent, that 30.83%, and divide it by 100. That will give me my weight. And now I have to multiply it by that big, ugly number that is the mass of a single copper 65 atom, which is 64.927793. And now I'm going to add the weight of my isotope 2, which is in this case copper 63, 69.17 divided by 100. Remember to take those weights, if they're in percentage form, you got to divide them by 100. And multiply it by the mass of the copper 63 ion, which is 62.929599. Okay, so that's really just how you set these up. Notice it's the exact same as I did before, which isn't bad. I just am using way uglier numbers. All right, so we punch that in and we do the math, and we would get that the average atomic mass of copper, and again, this is average atomic mass of copper, should be 63.5456. Okay, and we can actually kind of check if we have a periodic table, because this number should match at least really, really closely with what's given on the periodic table for copper. And indeed, 63.546, right? So that's pretty close to what we got, 63.546, 63.54, right? So the only difference is where they rounded. Okay, so again, this is the number, the average atomic mass. This is number on periodic table. Now, that said, if you're given this problem, you can you might be able to just go look at the periodic table. It should be very close But of course, I want you guys to know how to do the calculations. So I could give you, I could write a problem that was something like, on Mars, the percent distribution of copper is different. And so, basically you have to know how to do this calculation. Don't think that you should just go look at the periodic table. But of course, if we're talking realistically and here on Earth, that number will match the number that's on the periodic table.